I decided to make this video because I have an NES Zapper and I'd like to repurpose it for some other project ideas I've got. Since I don't want to plug it into an NES to play Duck Hunt, I need to understand how it works. And I mean really understand how it works, down to the level of the timing of the electrical signals and how exactly they're triggered. I went looking for information about the Zapper and found quite a bit. And some of the resources are really good. They made me feel like I really understood how the Zapper worked. But then when it came time to build something, I realized I knew almost nothing about it. It turns out a lot of the explanations are just too hand-wavy. So that's what this video is all about. I'm going to do a deep dive into the NES Zapper and explain how it really works, signal traces and all. First, I'm going to give a practical overview discussing exactly what causes it to trigger a hit and how you can duplicate that without an NES. I'll also talk about how the NES made use of the Zapper hardware, and I'll touch on why modern TVs can't work with it. After that, I'll do a hardware teardown to show you what's inside the case. I'll give you a circuit diagram and some suggestions for how you might modify the Zapper to use it for other purposes. Anybody see a duck? If you've ever tried to cheat at a Zapper game by pointing it at a light bulb and pulling the trigger, you'll know that that doesn't work. Unlike earlier light guns, the Zapper had some simple yet effective mechanisms designed to prevent cheating. And it's these mechanisms that keep it from working on a modern TV and that make it difficult to repurpose in general. The first safeguard is in the way that the Zapper detects light. It doesn't just trigger a hit when it sees brightness. Rather, it's changes in brightness level at a specific frequency. But before going any further with this, it's helpful to consider how this worked with an NES and a CRT TV. In Duck Hunt, for example, when the trigger is pulled, the screen will turn completely black for one frame. Then a white box is drawn immediately over where the duck was on the previous frame. Finally, gameplay resumes with either a hit or a miss being registered, depending on what the light gun saw. To understand what is really happening here, you need to know how a CRT TV works. When we look at the screen, we see an image, but it's not really there. We only see it due to persistence of vision. Inside the TV, an electron beam moves very rapidly to excite the phosphorescent screen, one horizontal line at a time. If we could slow it way down, it would look something like this. The current line being drawn is the only one that is actually lit up, and the rest are dark. Everything else is just a trick of the mind. So how is this relevant to the operation of the Zapper? Well, the NES picture processing unit generated 60 frames of video per second, and that was at a 256 by 240 pixel resolution. So doing the math, that gives 1 divided by 60 divided by 240 seconds to draw a single scan line. That's equivalent to a frequency of 14.4 kilohertz. Okay, so back to Duck Hunt. The Zapper has a photodiode that senses light. It does not see white boxes. It sees the initial black frame as darkness, then it sees the individual bright scan lines flashing on and off at 14.4 kilohertz. Assuming the barrel is pointed at them, it's this change from dark to bright at a high frequency that causes a hit to be counted. If this change in light happens at the exact right moment, when the frame containing the white square was being drawn and the trigger was pulled, you've got a dead duck. This also explains why the gun does not work with modern TVs. LCD TVs don't have an electron beam rapidly tracing out an image, but instead have individual LCD pixels that light up. And by comparison, they are very, very slow. Even a really high quality TV with a 1 millisecond pixel update time is about 0.001 seconds. That is way too slow. Take this program I wrote, for example. To the eye, it looks like an instant transition. But because it's an LCD display, the frequency is much too low and no hit is triggered. So if you want to repurpose a light gun, do you have to exactly mimic a CRT TV? That's what I wanted to find out, so I built this little test rig. First of all, here's the pinout of the Zapper's connector. There are just 4 pins, 5 volts, ground, the hit indicator, which is tied to the light detector, and the trigger signal. Both the trigger and hit lines need pull-up resistors. The trigger is super simple. Pull it and it grounds the signal. It's completely independent of light sensing, even though a lot of explanations out there link them. That is definitely not the case. To find out what exactly the light sensor responds to, I have a white LED that's being rapidly switched on and off at varying frequencies by this Arduino clone. The light shines right at the photodiode inside the zapper. I have it flashing the light at frequencies above and below the expected 14.4 kilohertz triggering frequency. I'm monitoring the LED switching frequency and the response of the hit signal with a logic analyzer. The bottom trace is the hit signal, and when it goes high, the light gun is registering a hit. So let's zoom in on one of these. And we'll see that it makes a transition when it goes to about 19.9 kilohertz. And on the other end of that, it makes the transition at about 13.5 kilohertz. So anywhere between about 13.5 and maybe 20 kilohertz, the light gun is going to register a hit. So there is a bit of wiggle room in there. All right, let's tear it down and see what makes it tick. Now, fortunately, they weren't too concerned with people opening these up back in the day, apparently, because you've got some screws that are easily removed to get inside the case. So I'll take care of that right now. All right, that lifts right off. That comes out of there. Just set these aside for later. And then this should just pull apart. You got to loosen something a little bit more here. Yep. Oh, one more screw hidden underneath the plastic trim. And now, there we go. Not a whole lot to it, really. So there's this lens that focuses the incoming light. And then this is really just a weight. This is a weight too. It makes it feel like you're holding something of value in your hands. And then there's a photodiode in here, but let's take a look at this circuit in a little bit more detail. So let me pull everything out. Got to remove some screws for this switch that's powering the trigger. All right, now everything should come out nice and cleanly. So let me unwrap this cord. And then the components should lift right out. There we go. So I can set all of this plastic casing aside now. All right, not a whole lot to it. So this right here, switch. It's just got those two wires coming off of it for when the switch is closed, feeding into this little circuit board here. I've already buzzed out these wires, so let me tell you what they are. Got some notes over here. So brown, right on the end, is ground. Blue is the hit indicator. White is 5 volts. And purple is the trigger. So, looking at the board, you can see the trigger feeding in right here, and then all you can really see are a couple capacitors, a few resistors, and it looks like a transistor here. And then you can't really see inside this. I think this is just a light shield. Looks like it's soldered to ground. And I assume that would just be because the case is going to allow ambient light through it. But it does kind of get in the way. Can't really see the rest of those traces, so I think that's going to have to come off, unfortunately. So let me do that. Safety first, or at least second or third. Soldering iron warmed up. Okay, starting to get some melting. See if I can wick that out now. Actually, get a better way to hold this. I don't want to have to put my fingers on it because it's going to get hot real fast here. Try this. A bit awkward, but I think I'll get it. There we go. Well, like that should do it. All right, let's try that again. Take 2. Looks like it's starting to wick up finally. Takes quite a bit of heat with that big shield on there. There we go. Well, that was a pain. Kind of expected it though. All right. Okay, I've cleaned things up a little bit so we can get a better look at this. So first of all, here is the trigger that's wired in right here. So you can see one side goes to the ground plane and the other goes to, looks like, let's see what pin we got here. The purple pin, which is the trigger pin, so that makes sense. So that's very simple. All this trigger does is ground that pin momentarily, just for that moment when you hear the click. So it's a very quick signal. And then the rest of this is going to be the more interesting part, which is the photodiode and the timing associated with it. So right there, at the end, you can see the photodiode, pretty obvious, and conveniently labeled PD43PI. Aside from that, it's kind of hard to tell what's going on. It's just a series of capacitors, resistors, and a transistor. But then there is this chip that apparently does most of the work. It is the Sharp IR3T07A. So I think that's going to be the key. So what I'm going to do next is map out this circuit, get a circuit diagram for it, and see if I can find out what this chip does, and then I'll get back to you and give you an explanation. Here's a better look at the hardware. There are a handful of components on the top. The bottom is nothing but traces. So I took a close look at this and came up with a circuit diagram. I'll show that to you now. If you want to grab a screenshot, go ahead, but I'll also put a link out there in the show description so that you can get a higher quality version of it. The star of the show is the photodiode that senses light levels. Of course, as we saw earlier, that is not enough to trigger a hit on the hit line. That is determined primarily by this chip. This is the Sharp IR3T07A. Unfortunately, this chip is completely undocumented. There's no data sheet, and nobody outside of 1980s Nintendo seems to know how it works, and they're not talking. So I would guess that the values of the capacitors and resistors might change the frequency that it signals a hit at, but I don't really know that. And I'm not going to try it because it's a whole lot of guesswork, and I don't know, maybe I'd fry the chip because I don't know how it works, and that would be a shame with a 40-year-old chip that's not in production anymore. So how can you repurpose this for your own applications? Well, it depends on what you're doing. So if you have the luxury of setting up an LED beacon, like if you're trying to control some device in your house with it, just flash it at the proper frequency. It's not as bad as it sounds because it's flashing at such a high frequency. It doesn't look like it's flashing. It just looks like it's dimmed a little bit. Now, if you're trying to do something like use this light gun with a modern television or a different console or something like that, you don't have that luxury. So what you might be able to do is clamp onto the anode of the photodiode. You could even route that through the hit line. And then what you would get is an analog signal showing the level of light. So I've got a trace where I took a look at that line. So you can see how you could interpret the lightness and the darkness to determine when a certain element on a TV screen, for example, is being pointed at. And then you could line that up with when the trigger is pulled and when the target is on screen to determine if there was a hit. Unfortunately, since the sharp chip is unknown, these are the kinds of things you're going to have to do. So it's not going to necessarily be a perfect solution, but I think there are some options to make this work with different projects. I hope you learned something from the video. If you did, please give it a like. Also, this is the kind of content I produce all the time, so have a look around my channel, and if there's anything else you like, please consider subscribing. Thanks for watching.